Hello. Today we are going to be implementing and verifying a 1-bit full adder using the schematic entry and RTL entry using the Intel Quartus Prime. Also, we'll be simulating the design using Questa and targeting the simulation or the synthesis to TerASIC DE1-SoC board, which has Alter Cyclon V chip. So our objective is to use the commercially available FPGA synthesis environment where we'll be designing a combinational circuit using the graphical schematic entry and then generating a RTL based on the schematic design. So once the RTL has been designed, we'll verify the code, RTL code, and then synthesize and analyze the code based on the FPGA constraints. We are gonna simulate the same design using a test bench and see how the design performs. On top of this, we are gonna create our own RTL design for the same 1-bit full adder and test the same thing with a test bench and simulate to verify the results and board resources that is gonna be consumed and compare both the performance. After doing all this, we are also going to be implementing a n-bit full adder for 4, 8, and 16 bits to see how many resources are being consumed in two different styles of designing. One is uh, behavioral and structural. So our primary hypothesis is behavioral design is going to consume less resources and have a better performance compared to structural. But we'll have to verify this quantitatively by designing and synthesizing for the board constraints. So here we are in the Questa application where I have designed the 1-bit full adder using the Quartus Prime's schematic entry. I've used the basic gates such as XOR, and OR gate to construct a 1-bit full adder where it takes A, B, and C in all 1-bit entry and generates sum and carry out by using the 1-bit full adder formula, a logical combinational formula. Based on this code, I've used the Questa's built-in tools where it will generate the RTL code based on the schematic entry. And that this is the schematic RTL generated from the schematic that I have designed, where you can see these are the inputs that I'll be providing, and these are the outputs that will be generated, and these are the three intermediate wires that connect between XOR to the next XOR, connects between and connects between XOR and AND. So all the different wires, they have been created as synthesized wires. So using these, the outputs of sum and carry will be logically generated based on these assigned statements. This schematic is going to be tested with the test bench where I'm providing the test vectors for a 3-bit entry starting from 0, 0, 0 and going all the way till 1, 1, 1. So this will test the design for all the logics with respect to A, B, and C in. The same thing we'll be monitoring using this monitor statement where for any change in A, B, C in sum or carry out, the monitor will display the statement with its respective value. Okay, so once the design has been compiled, we'll be provided with the compilation flow summary, which will have which will contain the information regarding the resources being used on the board. There'll be two summaries. One is on synthesis, and the other one is on filtering. Okay. First, we will verify the report generated by analysis and synthesis step. In this, we can see the logic utilization is 2 out of 32,070. That means we have used up two logical blocks for placing this entire logic. And going number of registers is 0 since we this is a combinational circuit which does not have any registers or flip-flops. Number of pins is 5 since we have used 3 inputs and 2 outputs. The number of pins dedicated to our design will be 5. And remain everything is 0, that is virtual pins, block memory, DSP blocks, and all the things will be 0 since this is a simple 1-bit adder which is completely in combinational logic. Going to the filter and filter place route report, even this will contain the same information since this is a simple purely combinational logic. There'll be no much optimization or filtering required since this is already a most simplified version of the full adder. Again, this will use two ALMs and 5 pins. Rest everything will remain 0. Okay, so once the compilation has been completed, we'll proceed towards RTL simulation, where our design and test bench will be used to simulate the design. So, so this is Quartus Intel FPGA simulation tool, and this is our full adder schematic. We'll go to compile and compile our test bench. So our test bench has been compiled without any errors. So we will go ahead and simulate the test bench. Okay. To simulate our test bench, first we'll select all the signals that we want and add them to the waveform window. Once that is done, we'll just run the simulation. Simulate, run, and run all. So as you can see here, we have the monitoring tool that has updated all the details for all the different test bench that we ran. Similarly, we can see the waveforms generated for the respective output. So the first two waveforms are for input A and input B. Third one is for C in, fourth is for C out, and fifth is for sum. For example, we can see when all the three are 0, sum and carry out is 0. When A is 0, B is 1, C in is 1, our sum will be 0 but our carry will be 1. And when all the three are 1, sum will be 1 and carry out will be 1. So our simulation has gone through each and every test case or the test vector and generated the respective sum and carry out signal. Now let us do the same thing but with a RTL code written by us instead of generated from the design. Here for the sum I have XORed the three inputs A, B and C in, and for C out I have given the same formula that we would have used for the schematic. So now we are gonna simulate the RTL code which is written instead of being generated by the schematic design. So again we'll have to follow the same steps, compile the design and generate the simulation tool. So for that we'll set this as the top level entry, run the compilation. Again this will go through the same compilation process and generate the report for us. Okay, so the compilation of RTL code has been completed and we can see that ALMs, there are two ALMs being consumed and there are 5 pins being dedicated to this design, which remains the same for both the schematic design and the RTL design. Coming to the test bench for this RTL design, I've made some modifications. Instead of manually entering the test vectors, I've created a for loop which will generate the values using this concatenation. So basically, this loop will run from 0 to 7, and for each value in the binary, the 3 bits of I will be assigned to A, B, and C in, thereby assigning A, B, and C in the values from 000 to 111. And same thing, we'll be monitoring all the changes and updating them to the output values. So let's go and run the RTL simulation, which will bring up the Questa application. So here in the Questa application, we'll go to work. Before that, compile, and we'll compile the test bench. Here we see there is no error compiling the test bench for the top module. We'll select the module that was compiled, that is the full adder RTL test bench, and we'll click simulate. This will bring us to the simulation window. Here you can see there are more objects, that is even the variable I can be seen here, but we are only concerned towards signals A, B, C in, C out, and sum. So we'll just drag these signals to the waveform window and click simulate. As you can see, these were the inputs A, B, C in, and the sum and carry out. When all the three are 0, sum and carry is 0. When A is 0, B is 1, C is 1, sum will be 0 and carry out will be 1. When all the three are 1, sum will be 1 and carry out will be 1. Same thing we can see in the waveform window, where the first is A, B, C in, the fourth signal is the carry out, and the fifth symbol is the sum. So thereby we have simulated the 1-bit full adder starting from schematic, generating its own RTL code based on the schematic, using a test bench to simulate that, and also writing our own RTL code based on the combinational logic, writing its own test bench and simulating that. We have also seen how many resources are being used at each step, whether it is the schematic that we are doing, or the RTL code that is generated based on the schematic, or our own uh, RTL written from scratch based on the combinational logic. Since this is a simple combinational logic, there was no variations in the report generated. That is, the number of ALMs, the registers, pins, or whatever are the resources that are being used for the board. So all remains the same for all the three logics, all the three different ways of doing this 1-bit full adder dedicated towards TerASIC DE1-SoC, which has Alter Cyclon V chip. Also for our RTL, whether it is generated from the schematic or the RTL that we have written from scratch based on the combinational logic, we can do timing analysis to verify what is the critical path and what is the overall time taken for the system to generate the output. This is evaluated by verifying the critical path. To do that, we'll go to Tools and run the timing analyzer or the time analyzer. Here first we'll do create timing netlist, which will evaluate the uh, propagation delay and all the details for the netlist. And we'll go down to report. We'll go down the report and select the report that we require to evaluate the propagation delay. That is report datasheet. So this will bring up the propagation delay. This will bring up the propagation delay that will contain the propagation delay from input port to the output port. In this, it will show we'll be able to evaluate which is the most critical part of the design. Here you can see from input A to C out, the delay was for 6.193 nanoseconds, but for the falling edge clock, it was 6.290 nanoseconds. By doing side-by-side comparison, we can see that for the port A to output port sum, the maximum propagation delay was 6.640 nanoseconds. So this path from A to sum will represent as the critical path, since this will be the longest time that takes for an input to be available to go through the combinational circuit and end up in the output. So this using this we'll also be able to evaluate the maximum frequency of the circuit operation. Based on this, the time delay of 6.640, we will be able to calculate the Fmax, and it comes out around 150 megahertz. So this will be the maximum frequency of the circuit's operation. If we try to design it anything beyond this, the circuit will not be generating our required outputs. We can do the same evaluation for all the three steps of our design. That was one based on the schematic, next is RTL from the schematic, and our own RTL. So there'll be slight variations in the result, but everything will be in a similar ballpark. Few things that we can see to vary is whether it is A to sum, B to sum, or C into sum. What dictate this is the timing constraints or the layout constraints the application will become. Since for this application or this experiment we haven't provided any timing constraints or layout constraints, the application will randomly select how the logical blocks are placed. Due to that randomness, we can either see A, B, or C in ending up in sum being the longest path. In my case, it happened to be A to sum. For others, it can be B to sum or C into sum. Okay, so we'll go to the second part of this experiment where we'll be creating a n-bit width parameterized RTL code for a n-bit full adder. We'll be generating this we'll be writing this code with a parameterized width targeting for 4-bit, 8-bit, and 16-bit. We'll also be writing it in two different methods. One is structural and the other one is in behavioral. Thereby, by doing this, we'll be able to evaluate how the synthesizing tool will synthesize a design based on the uh, coding style of the Verilog. So for the structural design, first we'll have to write the code for 1-bit full adder, where I've reused the previous design, where sum is the XOR of A, B, and C in, and C out is the logical uh, output of this formula. So based on this, this full adder, a 1-bit full adder will be called in a for loop from 0 to the width whatever we provide, whether it is 4, 8, or 16. So this 1-bit full adder is called for either 4 times, 8 times, or 16 times based on our parameter. And for the behavioral, I have created the design using A plus B plus C, the plus symbol as to represents the addition, and the result value will contain the sum data and the carry out data, and those are split again where values from 0 to width minus 1 will be saved as sum, and the MSB will be saved as the C out. Again, the behavioral here is parameterized with width value ranging from 4, 8 and 16. We'll be changing that for each compilation to see the result. To save the time for which is consumed for each compilation, that is for 4, 8 and 16 between both structural and behavioral, I've compiled the data and structured it into this table where we have three different bit widths, and in their respective structural and behavioral columns we'll be evaluating the number of logical units that are being used and its critical path. For 4-bit structural and behavioral, we can see reduction in number of ALMs and also similar critical path. There is not much variation in the delay. This is due to a 4-bit design being very small in size. So irrespective of the behavioral being making sure that the synthesis tool uses the dedicated fast carry chain, the delay will still remain the same since it is a smaller unit. But for an 8-bit, we can see some variations coming to that. The number of ALMs, we can see that they have reduced from 9 to 5, and as you can see, the delay has been reduced from 12 seconds to 8 seconds. We can see here for an 8-bit, the critical path has seen an improvement in the propagation delay because of the fast carry chain path that is being dedicated for the behavioral, since the synthesis tool can look ahead or while starting itself it knows that it is a full adder design and it can use the respective dedicated blocks. For 16, we can see reduction in number of ALMs from being 20 units from 20 units being consumed to 9 units. Whereas the delay for both of them remains the same. This could be due to the large size of this design. So yeah, that is the experiment that we performed on a full adder starting from 1 bit in its most user-friendly way of designing, that is a schematic design, extracting an RTL out of it, running a test for the RTL, then writing our own RTL based on the combinational logic, testing that using a test bench, simulating the and validating the result. From that, we expanded the experiment to an n-bit parameterized full adder, where we use the same RTL design in either structural or behavioral to run a 4-bit, 8-bit or 16-bit. Well, that's the advantage of having it as parameterized, where on the fly we can modify the behavior or the size of the adder without having to change the code. And also we quantitatively observed how the synthesis varies when the size is increased or there is a significant change in the way of designing, whether it is structural or behavioral. To see further reductions in delay or further reductions in ALM or logical units used, we'll have to either provide any timing constraints or layout constraints. By doing so, the synthesizer will be able to provide a better place and route options based on the constraints that we have given. Also, we we learned how to use this application to create our own RTL to simulate the RTL that we have designed. So yeah, we can say that we have achieved our objectives of creating a 1-bit full adder, an n-bit parameterized full adder, and learning how to use this Intel Quartus Prime application where we can write our own RTL, simulate that, synthesize that for our FPGA. So going forward, we'll be using the FPGA board, that is TerASIC DE1-SoC board, which has the Alter Cyclon V chip. So the upcoming experiments or the upcoming projects are gonna be intensive where we will be implementing our RTL onto the board. So yeah, stay tuned for that. Hopefully I'll be able to crack this down very quickly. So until then, have a great day. Thank you.